Now in this video, we're going to continue our discussion of applications of logarithms, and we will be considering finding models when we discover that our transformed data are linear. So we earlier talked about, in the last video, that there are many cases when the order of magnitude is the more interesting quantity. And so in those cases, we're going to think that the logarithm is going to be a more natural sense. So the values themselves are spread out multiplicatively, but once I take the logarithm of those values, I just have the order of magnitude, and now those orders of magnitude might have a nice linear relationship. So I want to consider the two main examples where we end up seeing a log transform being useful, and that is a power law and an exponential law. What I'll be doing is doing a transformation of the equation, and we'll discover that when I take the log of my dependent variable and then use the properties of logarithms on the formula of the model, that we discover that there's a relationship, a linear relationship in the logarithmic scale. So that's what we're about to do. So let's start with a power law. We have our model equation that my dependent variable t, I guess I should say that, here my variables, let's make a comment about that. My variables are t and s. So I'm modeling s is my x variable and t is my y variable. It's the independent is s and my dependent is t. Alright, so if I were to think about this equation, my model equation, and I'm going to be balanced, I have to maintain an equivalent equation, I'm going to take the logarithm both sides of the equation. And so I'll do natural log, the natural log of t, so that's the left-hand side of the equation, equals the natural log of the power law, which is some constant, that's a parameter, times my x variable s raised to the power p. Now, once I have this logarithm of the formula, I'm going to start to apply the properties of logarithms. So, my logarithm currently is a product. It's a product of my constant a and s to the p. So if I use the product rule of logarithms, I get the logarithm of each factor added together. So I have natural log of a plus the natural log of my s to the p power. And now I have a power inside of the logarithm, so I can use the power rule of logarithms to give me the logarithm of a that I had to start with plus p times the natural log of my variable s. And let me bring down the left-hand side that wasn't changing at all in these equations. And I want to highlight that on the left I have the natural log of t, and on the right I have the natural log of s. Those were my variables. And so let's introduce some transformed variables. I meant to use v, and it's equal to some number. Again, that's some number, natural log of a, plus a power, and then the natural log of s, that's again a variable, so let's call that a new transformed variable. So natural log of t and v are the same, and natural log of s and u are the same. And if I look at this formula, I want you to be aware that this is a line. It's the equation of a line. So in the sense that my p is a number multiplying a variable u. So this is like mx, a constant times my independent variable. And ln of a, that's another constant, so this is like my y-intercept of a line. So if I were to compare this, it looks a lot like the equation of a line. fact, it is identically the equation of a line. What we find is that a power law is linear in a log plot. My data, if I look both axes in a logarithmic scale and it looks linear, that means I'm working with a power law. And I can find the power by calculating the slope of that transformed data. So now let's do the same thing. What happens if I start with an exponential model? So we're going to do the same process. I'm going to start with t equals a b to the s. This is my model equation. And I will do balanced operations on both sides. I'll take the natural log of the left, which is the natural log of t, and the natural log of the right, which is a, b, to my independent variable. And a reminder that a and b are my parameters. Those are constants. S is my variable. So we'll do the same thing. We use our logarithm properties to give us equivalent expressions. So we have a product inside a logarithm, so we'll expand that as a sum of the logarithms of the factors. And now I have a power, and so I can use the power rule, and the natural log of t is the natural log of a, plus that what's in the power is my variable, times the natural log of b. So what's different about this exponential model, on the left it's the same. We have the natural log of our dependent variable. But if I look where my independent variable is, it's not inside the logarithm, it's just all by itself. And so I have, where are my constants? I've got a constant natural log of b, the base, and I have a constant for the natural log of a, that constant multiple. And again, this is the form of a line. So I've got y equals a y-intercept. Maybe I shouldn't use the same letter b, so let's do a different symbol, plus my independent variable times some number which behaves like a slope. So here's my slope, the natural log of my base, and the y-intercept is the natural log of the constant multiple. And we get a new relationship that if so notice, only the independent variable has a logarithmic scale. So let's summarize what we've learned. If I have a semilog plot, if a semilog plot of data is linear, the data follow an exponential law. And so what I mean by a semilog plot is that the x variable uses a linear scale, but the y variable uses a logarithmic scale. And if that looks linear, then y is exponentially growing in terms of x. Whereas for our power law, if they're both logarithmic axes and it looks linear, then we had a power law. Let's use the principles of logarithmic transforms to find a model. So here, suppose I have a model. So S and T are my data, and I have two data points, 35 and 240/30, and we want to say that this is a power law. And a reminder, so that means for us that the log, need to draw, the log plot is linear. Okay? So what we're going to do is we're going to create transformed data. So u is going to be the transformed variable s, and v is the transformed variable t. All right. And so my data, when st was equal to 35, that implies for me that my transformed data, we don't need to find their decimal values, it's the natural log of 30 and the natural log of 5. And my second data point, which is 240, 30, in the st variables, becomes transformed data. That's the natural log of 240 and the natural log of 30. Okay. Now, the point of the power law is that in the transformed variables we have a linear relationship, which means I can calculate a slope. So we need to find the equation of a line using a slope and a point. So my slope is the change in the output variable over the change in the input variable, and we'll just use our transformed values. So we have natural log of 30 from here minus the natural log of 5 from the first point. That's the change in the output, and then the same order, natural log of 240 minus natural log of 30. Now if I was just using a calculator and needed decimal values, I could calculate that and I have a number. I want to point out that we can use logarithm properties. What do we have? We have a difference of logarithms, and so we can write this as the logarithm of the factors divided by one another, 30 over 5. And in the denominator, what do I have? I have a difference of logarithms. So log of 240 minus log of 30, I can write that as a logarithm of the quotient. So when I simplify those fractions, all of a sudden I have the logarithm of 6 on the numerator and the logarithm of 8 in the denominator. Now a warning, don't try to simplify the 6 and the 8, because order of operations, it's not 6 divided by 8. It's the logarithm of 6, which is some decimal number, divided by the logarithm of 8. Alright, that's my slope. How do I find the equation of a line when I know the slope and I know a point? So we'll use a point. From earlier we had uv equals natural log 30 and natural log 5. So my equation of my line, v, the easiest that we'll find is if I take v minus the v value, natural log of 5, is the slope. So my slope was natural log of 6 over natural log of 8 times u minus the u value, natural log of 30. Alright, this is the equation of the line in the uv coordinates. But we want to think about the original st coordinates, and so we're going to transform back now. My v, remember, was the natural log of y. So we have natural log of y minus natural log of 5 equals this slope, natural log 6 over natural log 8, times natural log of x minus the natural log of 30. Awesome. Now, if we keep going, notice again we can use the properties of logarithms. We have a difference of logarithms. So I can write this as the natural log of a quotient, y divided by 5, is this constant, natural log of 6 over natural log of 8. And then again I have logarithm subtracted. I can transform that to the logarithm of x over 30. And finally, I want to point out that I've got a logarithm times a number. And so this number we can use the power rule. It becomes the power natural log of y over 5 is now the logarithm of my base was this x over 30, and it's raised to a power which is the natural log of 6 over natural log of 8. Well, notice what I have. I have a logarithm on the left and on the right, and so if I do the inverse equation, I get y over 5 is that base x over 30 to that power natural log 6 over natural log 8. I can solve for y if I multiply by 5, so I get y equals 5 times x over 30 to the natural log 6 over natural log 8 power. Alright, so this happens to be the first WebWork problem for your assignment, and so you can go through and create this solution. And the second problem is very similar to this with some different numbers. So go ahead and try those. And then the next we'll talk about the semi-log plot and how that relates to exponentials. Alright, for the last example we are considering an exponential law. So again, we're going to use the same variables, the same data points, but use a different model. So an exponential law model, here the idea is it's a semi-log plot. So s and the log of the dependent variable will be linear. We're going to follow the same basic pattern that we did last time. When I look at a semi-log plot and discover that it's linear, then we're going to think of s as our independent variable. So we don't need to change it, but we could. So s stays the same, but we're going to introduce a new variable for the natural log of t. So my transformed data, my point that started as 30, 5, is transformed to the same original data for s. The independent variable is not changed. I meant to change that to the number. S and v, the logarithm of t, is equal to 30 natural log of 5. And my second point, st, which was 240, 30, in the transformed coordinates, s stays the same, so we're still 240 in our independent variable, but we're natural log of 30. And the idea of a semi-log exponential model, we're saying that this transformed data is linear. Alright, so if that's linear, I can find the equation if I know, that's right, the slope and a point. Alright, so let's calculate our slope. Our slope is the change in our output variable over the change in our input variable. And so we have natural log of 30 minus natural log of 5. And then that's divided by 240 minus 30. Just as in our last example, we can think about the natural log of 30 minus natural log of 5. That's the difference of logarithms. So we can change that to a logarithm of the quotient. When I think about the denominator, these are ordinary numbers. This is a regular subtraction, so it's over 210. When we simplify that, I get the natural log of 6 divided by 210. That'll be my slope. And we use a point, so we're going to use a point, 30 and ln 5, and we are able to write down an equation that my dependent variable, v, minus the v value, natural log of 5, is equal to the slope, so that was natural log of 6 over 210, times my independent variable, s, minus 240. Alright, so the last step is to transform back. So we need to undo our transformation, and we'll think now that we have the natural log of t, that's what v is, minus natural log of 5 is this slope, natural log of 6 over 210, times our s minus 240. So I'm able to now rewrite the left-hand side. That's the natural log of t over s, or sorry, t over 5. And on the right-hand side, excuse me, I have the same, it's unchanged, natural log of 6 over 210, excuse me, times s minus 240. And we can make this look a little bit, we think, can we use our properties of logarithms? And we can if we see that there is a logarithm. So let's write this as the natural log of 6 times the fraction s minus 240 over 210. And now we've got a logarithm times a number, and so this number can become an exponent inside the logarithm. So we have natural log of 6, the base, raised to the power s minus 240 over 210. Alright, on the left we have a logarithm. On the right we have a single logarithm. And so I can create an equation without the logarithms using the inverse, and that gives me my model. So I'm starting to run out of space. Let me get rid of some of the slope calculation. And so we get t over 5 is the base 6 raised to the power s minus 240 over 210. And so if I multiply that 5 to the other side, I get a model t is equal to 5 times the base 6 raised to this power s minus 240 over 210. And that is an exponential model for my data. Alright, so the third WebWork problem matches this exactly. So you can go through this one. And then the fourth problem is similar to this, but with different numbers. All right. Well, I hope you have a good weekend.